Swayam Prabha. Digital India. Educated India.
We are halfway in the course. We have looked at in detail overview of fracture mechanics, followed by crack growth and fracture mechanisms. Then we also spent some time on energy release rate. Then we had a detailed discussion on crack tip, stress and displacement fields. In that we have completely covered the singular solution. We have started looking at the need for multi-parameter solution. Before we proceed further, it is desirable I try to clear as many doubts that you have in your minds. So, this we will have it as a discussion session and the class is open for raising questions.
In relaxation analogy, why do we use triangular region while evaluating strain energy?
If you really look at, we want to evaluate strain energy in the presence of a crack. See, it is not a simple task and we saw that it could be arrived based on dimensional analysis, relaxation analogy and finally actual calculation based on crack face displacements. In fact, only this would give the intended result, and this was taken up while we were developing fracture mechanics in the initial stages. So, the idea is to find out what is the real role of this relaxation analogy. You have to understand that as part of your learning process. And what you have here is, we know from our other considerations what is the strain energy in the presence of a crack. This result is known. With this result only we discuss the relaxation analogy. So, the focus of relaxation analogy is not just to get this result, but appreciate the concept that is developed as part of energy release rate. The focus is different, and let us look at what we have done. What we have done was, we have taken a plate of thickness B and we stretched it and we said introduce the crack at the center, and what was marked is note the area on which strain energy is released. Marking of this as triangle is only incidental. You could take a parabola, you could take a complicated curve, you could do anything of that sort. What it amounts to focus upon is, for the formation of cracks, strain energy in the neighboring area has contributed to the formation of two new surfaces. That is what is attempted to be shown. And what we have also done in the calculations, if you look at the calculation, I say volume of the triangle, I say all this, but I also bring in a factor called lambda. We have not evaluated lambda. See, if I evaluate lambda based on a triangle, then the question is valid, why triangle is so special? We have only indicated a region close to the crack contributes to formation of two new surfaces. We have said for thin plates take lambda equal to pi by 2. So, this absolves whether you take a triangle, whether you take a parabola, whether you take a complicated shape. The idea here is the region near the crack has released some part of the strain energy for the formation of two new crack surfaces. And why we look at the relaxation analogy? See, we are actually discussing what happens in the case of a brittle material, and I said while discussing relaxation analogy, imagine that you have taken a cycle tube, taken a sheet of rubber sheet and then pull it, then you introduce the crack and the crack opens up. So, what you will have to look at is, this is only to aid your visualization process, that energy can be released from the system for the formation of crack. And there are also many catches here. If you look at, we want to find out strain energy in the presence of a crack. How the crack was introduced, we have never discussed it. See, if I want to find out strain energy in the presence of a crack, it is a very difficult task to do. I said later on, when we have developed the displacements, I said you have to do a thought experiment. In the thought experiment, you find there is a crack, that crack opens up. What is the force that is required for opening up? That is the way we calculated it. Here again, if you look at, for me to have the crack to propagate, I should have introduced the crack, and after some length the crack would have propagated by itself from the strain energy of the system. And if you visualize it that way, this example is not complete by itself. Here again we are bringing in a thought experiment. The sheet was stretched and suddenly a crack opens up and you calculate the energy. So, the focus here is, for the formation of two new surfaces, strain energy in the neighborhood of the crack would have contributed to this. So, the focus is only to understand that strain energy of the system decreases to form two new surfaces, and that is the reason I also mentioned, what is logical is, when there is a crack extends by itself. When we found an identity between K and G, we did it very systematically. In fact, that is much more appealing to develop energy release rate. And if you really look at the literature also, people found it difficult to calculate the strain energy in the presence of a crack. That is the reason why Arvind suggested you go for compliance approach. So, when you go for a compliance approach, at least I can perform an experiment and calculate dC by dA. So, the focus of relaxation analogy was only to give you an impression that strain energy in the neighborhood of the crack would have contributed to the formation of the two new surfaces. See, in fact, even in your design courses, when you develop how to understand the concept of shear, suppose you take a shaft and put a keyway and put a key there, which is subjected to torsion, and you want to visualize that shearing action takes place on the keyway. If you are given a strong metallic key, it is difficult for you to visualize. One of the tricks that is employed there is, imagine the key is made of frozen butter, then you can visualize when the shaft is twisted, you will find that shearing action takes place. You are able to feel with the component in question. So, the relaxation analogy has to be looked at only in that perspective. We have not really made the calculation, we have just said lambda equal to pi by 2. So, that absolves, there is no special significance attached to the triangular area. I suppose you have got the answer now.
We know that energy release rate is energy required for unit extension of crack, whereas R is a resistance to fracture, but how G and R are equal in stable fracture?
See, you will have to look at what way we have developed the fracture theory. This is one form of representation which we had seen, where you find out sigma and root A is related to root of 2e gamma is divided by pi. This is one form of graphical representation. We also saw another form of graphical representation, where we had mentioned the resistance R is this much. In the case of brittle material, as you increase the stress, what you find is, at a particular value of critical stress, you have fracture instability takes place. So, here G equal to R. For brittle materials there is no problem. When we come to ductile materials, what we have noticed was, In the case of plane strain, R is not a constant, but it varies, but the variation is shallow. Here again, when does fracture instability occurs? When G becomes R, that is dictated by what is the stress level that you are imposing on the structure. When it is sigma 1, fracture instability does not occur, only when sigma 1 reaches sigma c, fracture instability occurs. So, you have the condition G equal to R satisfied. Let us look at for a plane stress situation. In a plane stress situation, what happens? The nature of R curve is totally different. It is very steep. When you have stress as sigma 1, the corresponding energy release rate is G1, which is far below the value of R. So, nothing will happen to the crack will remain as such. Suppose I keep increasing the load. When I increase the load from sigma 1 to sigma 2, that is a time where G becomes equal to R. So, now fracture instability is possible. Suppose the stress is raised to sigma 3. When stress is raised from sigma 1 to sigma 2, crack would not have propagated, but after reaching sigma 2, crack is ready to propagate. When sigma 2 is slightly increased, not sigma 3, even slightly increased, then you have a situation G equal to R, that is satisfied, but the current G is greater than the previous G. So, to that extent the crack will have a forward movement. Then as the stress level is increased, it will keep on moving like this on the graph, and when it reaches GC, any small increase would result in catastrophic failure of the component. So, you have to have the necessary condition is G equal to R, sufficient condition is dou G1 by dou A equal to dou R1 by dou A. So, in this zone only the necessary condition is satisfied. So, whenever the necessary condition is satisfied, the crack will propagate by a small extent, provided the load is increased. If the load is stopped, the crack also will stop, but once you come to this position, even a very small perturbation will make the crack to propagate catastrophically. So, what you will have to really look at is, you have a stable fracture followed by unstable fracture, and this is where I said when you are doing a plane stress test, you do not need to introduce a sharp crack like what you do in a plane strain fracture toughness testing. We would see that as part of fracture toughness testing, because in all plane stress fracture toughness testing, you have a natural crack formation because of stable fracture, then it is followed by unstable fracture. Now, let us come to the question. In the case of fatigue, the crack takes finite time to grow. In an actual practice, you will have stable fracture followed by unstable fracture, there will be hardly any time. For pictorial representation, it is shown as if sigma 2 is so small and sigma c is so high. This kind of a graphical representation is shown to illustrate the point. So, whenever G equal to R, to satisfy this condition, when the energy is released, you will find some small extension of crack has to take place, but that would not be catastrophic. That is what is discussed upon.
Whether the resistance and fracture toughness are they same?
You know, we have looked at the graph for the plane stress as well as plane strain. Now, we look at the graph of this plane stress. See, this is the resistance present in the case of the material. As the crack advances, in the case of ductile materials, what you find is you have plastic deformation, and this plastic deformation size increases. So, as the crack length increases, the resistance also increases. So, when we talk about resistance, you have to look at what happens in the case of brittle solids. Brittle solids, there is no plastic deformation, the resistance remains constant, which you could take it as a property, whereas resistance is used as a conceptual appreciation how the material responds. In the case of plane strain, it is shallow. In the case of plane stress, it is very steep like this. It is very steep like this. And if you look at fracture toughness, what do you say? Fracture toughness by definition, it is a material property. And if you look at for plane strain case, it becomes a material property, and if you exceed stress intensity factor greater than fracture toughness, you will have catastrophic failure. We will also see in the fracture toughness testing variation of fracture toughness as a function of specimen thickness. So, you will find out for different thicknesses what is the value of fracture toughness when you look at the plane stress case. So, when you say fracture toughness, it is a material property. When you say resistance, what actually happens, how the material behaves in actual practice. So, R curve is a concept which is beautifully developed to explain various things that you come across in fracture mechanics, like stable fracture followed by unstable fracture, and the case of intermediate plates you have this pop in behavior. So, R is different to denote the resistance provided by the material. When you say fracture toughness, you recognize that as a material property like yield strength. When you say yield strength, you have certain connotation how to understand that. So, similarly, when you say fracture toughness, you look that as a material property. Resistance also the behavior of the material, but it is little more elaborate, because you have a R curve as a function of crack length. You do not have that kind of information, you have fracture toughness as a function of thickness of the specimen, not related to the crack length. So, this is the way you have to look at it. Yeah.
Sir, as you define the stress concentration factor as a stress region near the geometrical discontinuities, similarly, how can we define the stress intensity factor theoretically?
I would like to correct your question also. See, you have mentioned stress concentration factor as a stress raiser. It is not so. When you have a geometric discontinuity, that acts like a stress raiser. When you have a geometric discontinuity, for example, if you take the case of a infinite plate with a elliptical hole. So, I have a cutout here. So, this is a geometric discontinuity. Because of this, what you find is you will have a maximum stress developed at the tips of this ellipse, and that is given as sigma y max equal to sigma into 1 plus 2a by b, where a is the semi major axis of the ellipse and b is the semi minor axis of the ellipse. And what you will have to look at is how the stress concentration factor was understood in the initial stages. There was lot of debate between mathematicians and engineers. Mathematicians said an infinite plate with a small hole is equal to an infinite plate. They did not recognize that because of a cutout, it would introduce certain changes in the stress field. That is point number 1. Point number 2 is the stress levels will increase was a recognition by the solution of Kirsch for a plate with a circular hole and Inglis for the case of a elliptical hole. And what you will have to realize is, suppose I do not have a cutout, when I have a uniaxial stress, I would still have only uniaxial stress field in all the regions. The moment I bring in a cutout, the stress field changes, it changes to biaxial. This is you have to recognize first. And the second issue is you have a very high value of stresses developed, and that is also noted. So, people said the moment you have any geometric discontinuity, it is potentially dangerous from the point of your design approach. You have to take that into account. How do you take that into account? You have to have some kind of a methodology by which it says the stress levels are very high, and then you need to accommodate that in your design calculation. From that point of view, stress concentration factor was introduced. For many problems, if you look at the definition of stress concentration factor from theory of elasticity, it says the maximum stress divided by far field stress. That would be greater than 3 for many finite bodies. It would approach something like a factor of 9 or so, but it would not increase beyond that. For many of the common design problems, that is how people have looked at the stress concentration factor. On the other hand, when you look at the case of an elliptical hole, English alerted when B tends to 0, the stresses go to infinity. Now, you may ask a question, I think the question has really come. Even in fracture mechanics, we say sigma y goes to infinity. So, what is so special? There you call it as stress intensity factor, here you call it as stress concentration factor is not valid. If you really look at stress concentration factor, definition fails when B becomes 0. So, you need to have a different type of parameter to explain what happens in the presence of a crack. What was the outcome of English solution? English said even a very small crack, even for very small load, the stresses would be infinity and fracture would take place. After having listened to Griffith's analysis, now you are very clear you need to have a finite length of crack which has to be a critical value for a given stress applied, only then crack propagation takes place. So, what you have is, in the case of crack problems, your conventional representation of stress concentration factor is not sufficient. You have to bring in a size factor. The size factor here is length of the crack. So, you have sigma root A is a parameter bundle which you call it as stress intensity factor, which has dispelled the anomaly created by English solution. It has brought in length of the crack is also very important. So, you have to look for a critical crack length and a critical associated stress. So, this is the fundamental difference between a stress concentration factor and stress intensity factor, and we have also seen a mathematical definition. So, we have looked at the mathematical definition two different ways. One way is we have related this to the stress function. In fact, we are going to discuss in the next chapter, if a stress function is given, how to find out the stress intensity factor. So, you have a mathematical definition. So, limit z naught tends to 0, root of 2 pi z naught multiplied by the stress function capital Z written in terms of z naught. So, when you solve a problem and find out what is the definition of stress intensity factor in terms of the parameters of the problem, then you will appreciate. So, stress intensity factor really brings in the role of a crack and how it affects the structure. And there are a lot of differences between stress concentration factor and stress intensity factor. One of the first things that you can notice is it has a very funny units of MPa root meter, whereas stress concentration factor has no such units, it is just the number. And another one what we have looked at, we have also looked at the strength of the stresses near the crack tip vicinity is solely dictated by the stress intensity factor. So, from that point of view, you could also define stress intensity factor for each of the modes like this. So, you look at the stress component sigma yy at theta equal to 0 multiplied by root of 2 pi r, take the limit r tends to 0. So, you have a mathematical definition how to get stress intensity factor K1, how to get stress intensity factor K2. Here you take the role of shear stress tau xy. For the stress intensity factor K3, you look at the antiplane shear stress tau yz. So, this brings out what is the essential difference between stress concentration factor and stress intensity factor.
So, when you have shown the photoelastic fringes nearer to the crack tip are not forward tilted, but the fringes away from the crack tip are forward tilted. Whether this forward tilting indicates the crack advancing direction, and why the fringes nearer to the crack tip are not forward tilted?
This is good question. You are primarily getting this kind of a doubt because I find half the class is exposed to experimental stress analysis and half the class is not exposed to experimental stress analysis. So, I will use this opportunity to explain certain fundamentals of photoelasticity that would aid your understanding. So, we will look at that as well as the specific question you raised regarding the fringe pattern. First of all, let us look at how photoelasticity is used in fracture mechanics. I have always been mentioning whatever the stress field that we obtain, whether they are suitable for a given situation was established by the technique of photoelasticity. Then the question comes how. So, we have to know what do the photoelastic fringes really represent. In photoelasticity, one observes contours of constant principal stress difference, which are labeled as fringes, and these are known as isochromatics. And how are they mathematically related? I have the maximum shear stress is given as square root of sigma x minus sigma y whole square divided by 4 plus tau xy whole square. Suppose I solve a problem analytically, then I would get expression for sigma x, sigma y as well as tau xy. So, from that solution it is possible for you to calculate the quantity maximum shear stress. Then you can also plot this as contours. When you plot them as contours, you can compare it with experiment and then see whether your analytical equations are correct. So, before we go into that kind of an approach, we will look at how we understood what is photoelasticity. I took up a very simple problem of a beam under 4-point bending. For this problem, from your strength of materials approach, you know the stress field as a closed form solution in the region away from the points of loading. The stresses vary linearly, and we have identified what would be the nature of contour sigma 1 minus sigma 2. This is the way I introduced photoelasticity for you, and we have been able to establish the contours of sigma 1 minus sigma 2 have to be horizontal lines. This we have done it based on analytical calculation, because the field is known, you know the solution. So, it is simple for you to establish how the contours will look like. Then what we did, we directly looked at the fringe patterns obtained for the similar problem. And how do they look like? They are horizontal. So, from that we have concluded that whatever the contours I get in photoelasticity are contours of sigma 1 minus sigma 2. And what I will do is I will go a step further and then give this information as well. In the case of photoelasticity, light is used as a sensor, and the equipment that you use for visualization is a polariscope, and in fact, photoelasticity provides two basic information. It provides contours of sigma 1 minus sigma 2 as well as the orientation of principal stress direction. As we are not required to use this in this course, I did not emphasize it earlier, but now we will also have a brief look at that. And what is a physical principle? Each of these techniques is governed by a basic physical principle, and what you find is certain non crystalline transparent materials, notably some plastics, are optically isotropic under normal conditions, but become doubly refractive or birefringent when stressed. So, this is the basic physical principle, and a crystal by nature it is a birefringent material, whereas here the birefringence effect is temporary. As long as the loads are maintained, it will behave as doubly refractive. When the loads are removed, it will behave as optically isotropic. So, whatever the loads that are introduced, that really cause this to behave in a birefringent manner. So, by looking at the birefringence effect, we can calculate the stresses. That is the basis of what photoelasticity is. And how does the equipment look like? I have an equipment like this. I have some piece of optics, we will not get into that. I have a disc under diametral compression, and when I rotate these elements, I would see one stationary contour and another moving contour. And I said photoelasticity provides contours of sigma 1 minus sigma 2 as well as principal stress direction. So, in a simple arrangement called a plane polariscope, you will see isochromatics as well as isoclinics. I have taken this to show when I use a monochromatic light source, I would see the fringe patterns as black and white, because for all our analytical calculation we have only plotted black and white. Suppose I change the light source to white light source, you will see these contours as colored and one set of contours that is remaining black. So, that is a technique to identify quickly what is an isochromatic and what is an isoclinic. And there is also another optical arrangement that you have, where you have two more additional optical elements which help you to remove the isoclinics, and you will see only isochromatics. And this is the kind of optical arrangement that we have used in fracture mechanics to get the relevant fringe pattern. And what you will have to notice is the experimental fringes, the thickness varies. If you see here, the thickness is very broad here. When you say a contour, you will have only that as a line. What you have to do is, where you are plotting the fringe order, we will have to give a small variation and analytically plot that, you will automatically get a thickness variation. You have papers written on that, you could look at the references. So, this gives you, if you know sigma x, sigma y and tau xy, it is possible to plot. Now, let us look at what was the solution from Westergaard. The Westergaard solution was something like this. When I plotted the fringes, how I have got the fringe patterns symmetrical about the x axis as well as the y axis. In fact, if my experimental fringes are also like this, we would not have discussed modified Westergaard equations, and then now we are looking at the generalized Westergaard equations, all of them we would not have looked at. What we saw in the case of mode 2, in the case of mode 2, I have a fringe pattern like this, which is experimentally recorded. When I look at Westergaard solution, I have this, the singular stress field itself gives a fringe pattern which is very similar to what is there in the experiment, and in fact the second term was 0 here, that also I mentioned it. We would see that when we develop the generalized Westergaard equations as well as Williams corner function. The moment go to mode 1, when I have a short crack like this, I have my fringes tilted, and they are tilted forward in this case. And how the tilt was, if you look at very carefully, I have the tilt like this. As you go close to the crack tip, they are becoming straight. So, by raising this question, I appreciate that you have observed this phenomena. What way we can interpret? Suppose I have fringes which are straight, then I could say I could still use Westergaard solution in that zone and process the experimental result. When I have a tilt, then I have to have Irwin's modification, only with that I can interpret the data. And if you really look at the fringe pattern, the zone where it is straight, it is so small, it is very difficult to collect data from that zone. And we have also seen one more aspect. In the case of RDCB specimen, that is rectangular double cantilever beam specimen, I have the fringes tilted backward. It is backward and it is becoming straight near the crack. And what I find here, in this case as well as in this case, I could interpret the experimental data by having just an additional term introduced by Irwin. Suppose I go to a real situation like a crack emanating from outer boundary of a pressurized vessel, I have a frontal loop. So, I have a variation of fringe order along the crack axis, which is shown as a blow up. On the other hand, if I have a crack from the inner boundary, I have a situation that these fringes are tilted backward and these fringes are tilted forward. So, I have a combination of backward and forward tilted fringes. Even in that case, I need to go for multi-parameter solution. That is why I have shown both of them in one slide. I have crack emanating from outer boundary, I have crack emanating from inner boundary. Though I could get some value of k by processing only the forward tilted fringes which are closer to the crack tip, a reasonably accurate solution is possible only when I have modeled all the aspects of the fringe pattern. So, that cannot be modeled by Westergaard, neither by Irwin's modification. So, you have to go in for multi-parameter solution, which we would develop in the next class or so. Then we would see that the solution would be quite useful.
Sir, when you have explained the Westergaard solution, you mentioned that it is applicable only for a biaxial state of stress and not for uniaxial loading. However, it is used to represent the stress field in uniaxial case too. So, could you please explain it again? Also, will stress in horizontal direction play any role when crack advances?
It is a good question. See, let us look at what we have discussed as Westergaard solution. If you look at the boundary conditions, we have clearly taken a biaxial loading situation, and from that we have got the Westergaard stress function. And if you take the stress function in this form, sigma z divided by root of z squared minus a squared, this is an exact solution, in the sense it can be considered as a closed form expression for the field. Mind you, if you have not looked at generalized Westergaard, you would still not accept this as a closed form expression. See, what we have got here is, it definitely satisfies, if I take the stress function in this fashion, satisfies the stress free boundary of the crack as well as biaxial loading at infinity. This stress function takes care, but it also says tau xy equal to 0 along the crack axis. Leaving that issue apart, it satisfies the boundary condition near the crack faces as well as what happens at infinite boundary. See, in theory of elasticity, we are accustomed to looking at closed form expressions. That is the time where fracture mechanics was developed. What was the focus by Irwin? He said, you do not worry about the crack, worry about the crack tip. He shifted everything to the crack tip. The moment you shift your origin to the crack tip, you get a final expression like this. Though you have selected this satisfying the outer boundary as well as the crack free surfaces, finally you shifted the origin to the crack tip, you made a simplification that z naught is very small compared to the crack length, and finally you arrived at this kind of stress field equations. And how do these stress field equation model the scenario? It is based on a stress function like this, and if you look at when r tends to 0, sigma x equal to sigma y and reaches infinity. In reality it would not reach infinity because of plastic deformation, you will have some value dictated by the whatever the plasticity condition that should prevail here. When you go to infinity, what happens? When you say r equal to infinity, it goes to 0. What does it mean? It is not an exact solution for any problem of practical interest. Then why it is so important? See, what you will have to keep in mind is the solution what we have got is a singular solution, and this is valid in a close vicinity of the crack tip. You are only looking at the remote loading. The remote loading loses its significance as long as the crack faces open up. In the near vicinity, how near, that is problem dependent. We are not qualifying what is the value of that distance, that is problem dependent. People have found out that singularity dominated zone size varies from problem to problem. In that zone, this solution is reasonably accurate. So, if you are focusing your attention only in a region close to this, as a singular solution, people have used it interchangeably for uniaxial as well as biaxial. If you really make the fundamental question, what happens when r tends to infinity, this solution says only 0. So, what you will have to keep in mind is this is a near field equation. If you understand that this is near field, not a closed form expression, then using this in an uniaxial situation is also reasonably okay. But people have made certain observations which are quite not right. Irwin introduced a term minus sigma naught x, and what we find in the literature, people initially reported when you say sigma naught is equal to sigma, when you put this at infinity, this goes to 0. So, this could be used for uniaxial loading situation. That interpretation is strictly not correct, because if you say r equal to infinity in this solution, there is no stress in the y direction. What way you have to look at Irwin's modification is, from the experimental fringe pattern, find out sigma naught x as well as k1 for a given problem, and for all your fracture mechanics calculation, use the value of k1 which is obtained by solving both the parameters from the experimental fringe pattern. Once you look at the situation like this, for finite body geometry, you will get a complicated fringe pattern. We will not stop at sigma naught x, we will also look at multi-parameter solution. That way, for all finite bodies, you will be able to find out the solution by calculating all the parameters involved. So, what people have done is, in the initial development, people were trying to find out, they were actually groping in the dark. So, they have to get some kind of a solution and carry forward. So, if you focus your attention very close to the crack tip, the distinction between a biaxial loading or uniaxial loading, it no longer is so strong. I mean, there is a distinction exists, but unless you take a multi-parameter solution, none of the solutions are valid. And that is the reason why you find nowadays people also have looked at fracture theories involving higher order terms. People have used the second term, which is called as T stress, and let us look at what is the role of this stress, because that is the another part of the question that he has asked. So, if you look at the addition of sigma naught x stress term, you have to notice this does not introduce any singular stress at the crack tip. This is observation number 1. What is observation number 2? It definitely affect the stress state in the body. How does this do? If you are going to calculate the magnitude and the direction of the principal stresses, they are influenced by the additional stress. You cannot ignore it. See, we are going to discuss towards the end of this course theories related to which way the crack would propagate. If you look at only the singular solution, you will have in the case of mode 1 what is known as self similar crack propagation. If the crack was horizontal, it will propagate in horizontal direction, but people have found turning of the crack also occurs in the case of mode 1. How do you go and explain it? Unless you bring in higher order theories, such things cannot be explained. So, in the initial stages of fracture mechanics development, if you are confining your attention only to the close vicinity of the crack tip, use of the term sigma x really does not affect, because the crack opening stress sigma y in the neighborhood of the crack tip that dominates the behavior of a cracked body is not affected. So, from that point of view, it is justifiable, but you have to keep that after looking at generalized Westergaard equation, none of these solutions are accurate. You have to go for multi-parameter solution for any problem of practical interest.
Sir, regarding the Westergaard solution for a crack opening displacement, it is uy is equals to 2 sigma by e root over a square minus x square, but this has been used in the problem for solving superimposition of 2 uniaxial stresses. How can this be used?
Your question also borders on why do we use a biaxial loading situation to uniaxial loading situation. Let me put back, see, this representation comes from mainly because at the time when these theories were developed, people were looking at hole in a tension strip, elliptical hole in a tension strip, and Griffith also developed his fracture strength based on uniaxial loading. So, people are trying to find out in the presence of a crack how to find out the energy release. They have to look at the crack plane displacement. So, they simply took the crack plane displacement that was available, put it into this problem, and then found an answer which was satisfying. Now, after learning all of those development and also the developments which are current, what you can really look at is whatever the result that I have used, I can replace this diagram by a horizontal loading also, and then apply this. The situation is same whether it is a uniaxial loading or biaxial loading. We have used the biaxial loading result. Only for a biaxial loading result, we know the definition of K as sigma root pi a. It is not a definition for uniaxial strictly. So, from that point of view, you have not done any mistake. But if you look at any book on fracture mechanics which are currently available, all of them have this so called defect which you have rightly pointed out. That is what I would say. Whenever they look at energy release rate based on crack plane displacement, you will only find uniaxial loading depicted. So, this also follows in the very close vicinity of the crack tip, as sigma y is not affected because of sigma x, and you are really looking at v displacement, you are not looking at the other displacement component. So, people have used it, but whatever the result that we have got, that is G equal to K squared by E, that remains same. So, that is the reason why I said in the class was, when you had a single crack, extend it by a little and close it, that is the best way to identify the interrelationship between K and G. this was only historical, finding out the energy release using this crack phase displacement was only historical note, and you can actually put horizontal stress component here, the result is valid, and ultimate interrelationship between G and K still remains the same. So, what you will have to keep in mind is, in the initial stages of development, people are focusing only to the crack, and they were used to looking at uniaxial. Because of the force of habit, they have also used it, and that is a way I think we have to take it. Can you allow one question?
Sir, for deriving parameters like energy release rate and stress intensity factor, we have assumed a crack as through crack, but in many of the engineering problems we encounter crack as embedded crack or cracks originating from surfaces. Whether the derivations are applicable to embedded cracks also.
See, it is a very good and practical question, because in most of the engineering applications crack appear from surface or you have embedded cracks. So, this is the way you have, and when you have this kind of situation, our ultimate objective is also to apply fracture mechanics to these difficult situations. We have to start somewhere. So, throw cracks are easier to handle analytically. So, we develop methodologies for throw cracks and graduate to apply them for embedded cracks as well as to surface cracks. So, that is the way you have to look at it. The concepts will be applicable, but actual calculations would be different, and in many cases you may have to depend on numerical approaches or experimental measurements for you to solve the problem, because those geometries will become very complex and you have to depend on sophisticated numerical code or experimental measurement for you to address those issues. We will definitely graduate to that. We will not stop with throw crack situations alone, because even in your bending I have been mentioning, you start from a constant bending moment, then we graduated to variable bending moment, constant shear, variable shear, and I said that it introduces certain difficulties which we saw result from theory of elasticity, but the basic kernel is understood. In a bending situation, the stresses would vary linearly over the depth of the beam is a very key information. So, similarly in the case of a crack, what happens when I have a throw crack, I have a straight crack front. We have understood stresses would be singular, but the singularity would remain same on the crack front. The moment I go for surface crack or embedded cracks, I have a curved crack front. So, the stress intensity factor would vary along the crack front. So, the problem is much more complex. So, you have to wait for the subject matter to be developed. We would definitely look at those issues as part of this course.
Whether the forward tilting indicates the crack advancing direction?
See, the answer is no. I would show two situations. In the case of SCN specimen, you find the fringes are forward tilted. I have a crack axis like this. This is actually the crack, and this is the place where the crack can advance. And if you look at RDCB specimen, I have a crack here and crack can advance in this direction. In this case, the fringes are forward tilted. In this case, fringes are backward tilted, but in both the cases the crack would advance in the forward direction. Later on we will go and show that it is indicative of the triaxiality constraint. It is nothing to do with crack propagation direction. It is dictated by triaxiality constraint. So, which you will have to wait for some time and appreciate.